dear colleagues and dear friends, this time I will present what we have done with the steels. This is a special kind of steels which are made for elevated temperature application. Their designation is P91, and we have investigated the behavior of the heat-affected zone of those steel grades. If we deal with a high temperature or elevated temperature under the stress, then we have the phenomena known as a creep. In order to have this loading, which we call creep, we need to have the progressive loading, which is time dependent. It means that the material will be less and less strong as we apply the loading during the longer operating time. When I say longer operating time, I mean much more than 50,000 operating hours. In Serbia, where I came from, the power plants were operating with the old steel grades around 120,000 operating hours without stopping. But what we had the operating temperature only around 500 degrees Celsius or 550. Because we all want to preserve the environment, we have to increase the operating parameters of steel. It means if we increase the operating temperature and if we increase the operating pressure, then we will save a sort of saving of energy. It means that we have to choose new steel grades which could stand temperatures around 600 degrees up to 620 with the steam pressure of 270 megapascals. 270 bars, I'm sorry. It means 27 megapascals, I'm sorry. Okay, just have a brief look at the creep diagram. So, the creep is consisting of 4 regions. The first region is here. We call it the instantaneous elastic deformation. After this elastic deformation, that will happen once we go to the, let's so-called, first stage of the creep, when we have the velocity of the creep, which is increasing with the increasing of strain. After some time, because this is the time dependent, as we said, after some time, we enter in the region number 2. This region number 2 is called steady state creep region. In this steady state, we can say that we have almost constant velocity of the deformation, which is called creep. And finally, the last region, the region that we call the third region of creep, we have the phenomena that the velocity of the creep is increasing, but in the 7th moment of the time, so we can reach the failure or the final fracture very quick as we enter in the region number 3. The new generation of steels was produced in Europe in the middle of the last 20th century, and it was produced also in Japan and also in the United States. But here, this grade 91 that we have was produced in Germany, and we are going to investigate this, let's say, German steel. So, the microstructure of the base material, unaffected, that we call virgin material, with 0 hours of operating, is, as you see, this is a microalloyed ferritic steel, which is alloyed with a little bit of vanadium and niobium. And it is very important to have a very controlled percentage of nitrogen and also of boron. Main application of those steels is in the thermal power plants. It means in boiler superheaters, in reheaters, in tubes and in pipes of power plants. Then, in special elements like headers and steam piping, which are for high temperature use. And we can also use this grade of steel in the furnace tubular in the petrochemical industry. The old steel that we had, which was operating over 100,000 of hours, but at the low level of temperature, we call this steel grade 22. It was molybdenum vanadium steel, also German steel, and we call it the grade 22. Now, let's see, what are the advantages of the new grade P91 over the grade 22? First of all, it is excellent strength and excellent creep behavior at the elevated temperature, which is extremely important. Also, we have the increased corrosion oxidation resistance at the high temperatures with those steel grades. With those steel grades, I will show you later the diagram, we can reduce the thickness of the wall. So we can reduce all the weight of the old pipeline and tubes, and we can, of course, reduce the costs. And we also have the improved, very important thing is the improved resistance to thermal fatigue. So, we can say that steel 91 has a very good heat transfer and also has a low expansion coefficient compared to the previous P22, which was the austenitic steel. This grade of steel was austenitic one, and this that I will repeat is a ferritic steel. So this low thermal expansion and the high thermal conductivity are very important for thick walled components, which are very susceptible to thermally induced stresses during the period of startup and shutdown. Startup and shutdown, those periods are exposed to the low cycle fatigue loading. Okay, this is this diagram that I wanted to show. With the old molybdenum chromium vanadium steel that we call P22, the thickness, when we have the same diameter, inside diameter of 200 millimeters, and the same temperature around 600 degrees, with the same pressure of 32 megapascals, we need the wall thickness with the old steel of over than 100 millimeters. But if we use this steel that we were investigated, P91, the wall thickness will be reduced to only 45 millimeters, as you can see. So our steel is now alloyed also not only molybdenum and vanadium, but we have niobium, and as I told you, we had nitrogen and boron also. In the welded joint, as you can see in this figure, the welded joint, you know very well, consists of 3 regions. In the middle, we have the weld metal. The rest is base metal. But in between them, we have this very susceptible and very weak region that we call heat affected zone. If the welded joint is exposed to elevated temperature application, we have a phenomenon that we call 4 type of cracking. In the middle of the welded joint, in the center, we have type 1 cracks, which are going only through the welded material. And this is well known as cold or hot cracks. The other type 2 of cracking, are the cracks that can start in the weld metal and they can penetrate in the heat affected zone. Type 2. Type 3 cracking are cracking which affects only in the heat affected zone and in the fusion line. Fusion line is the border between weld metal and heat affected zone. This is the fusion line, and here we have the cracks designated as type 3. What is for us engineers very dangerous are the cracks type 4. Type 4 cracks, here they are in the red color, designated in red color, are extremely dangerous because they start in the heat affected zone, but in the region of the heat affected zone, which is called intercritical region, and they penetrate to the base material. Thanks to those cracks, the operating life of our power plant component can be decreased from 100,000 hours to only 30,000 hours. We will see why. So, this is the welding diagram, typical for the regions that can affect in the steel, which is called elevated ferritic application steel. So, the first region, which is behind the weld material and behind the fusion zone, this is the region which we call coarse grain region. And this coarse grain heat affected zone can appear between 150 and 1150 degrees Celsius. And after that, we have the phenomena that we called the tempered phenomena called recrystallization of the grain. So we are slowly moving from the coarse grain to the smaller, finest grains. So we are now in the fine grain heat affected region. And in this fine grain heat affected region, we have those cracks type 3. But as we move to the lower temperatures of the welded joint, we have these partially transformed heat affected zone, which we call intercritical heat affected zone. It is very near to the base material, and you know that the base material is unaffected by welding. So the cracks type 4 start in these intercritical regions, and they grow and they penetrate into the unaffected base material. How do we investigate only this intercritical region? As engineers, you know very well that the heat affected zone is very narrow, and it is very hard to make the specimens from the real welded joint. It is very hard because this heat affected region can be very narrow. And if we want to put the notch, or if we want to put the crack in the heat affected zone, we are never certain if the crack is where we want it to be. That is why we are doing something which is called thermomechanical simulation of welding. And this is what we also called, thanks to the device, a Glebel simulation. The Glebel device for thermomechanical simulation allows us to simulate every single region of the heat affected zone. If I want to simulate the coarse grain, I will do the specimens around 1500 degrees Celsius. If I want to simulate the intercritical heat affected zone, I will do this at lower temperature, which are 950 precisely. In our case, in my case, it was 925 degrees Celsius. So this is the block diagram. What we have, what steps we have to fulfill to have this thermomechanical simulation. For example, for the beginning, we have to know the CCT called temperature diagram of the base material and of the weld metal. And according to this CCT diagram, we can calculate the weld thermal cycle curve. When we do this, we know the exact regime of the simulation for this zone. So we put our specimen in the device which we call the thermomechanical simulator, and we do the simulation, which will last in depends of delta T TH. It means the delta TTH is the time between the transformation between 800 and 500 degrees. So our experiment with one specimen will last, let's say, around 30 to 50 seconds. After that, we take the specimen, and it is extremely important to put it into the furnace and to do something called post-weld heat treatment. Post-weld heat treatment is extremely important for all the steel grades P91. You will see why. After that, we can do the mechanical testing, the fracture mechanic testing, everything we want. And after we make a fracture service, we will investigate it on the optical microscopy, scanning electron, or transmission temp microscopy. Okay, so that's what we did with our specimen. We did the testing, a lot of number of specimens, but we conclude that the intercritical heat acidic zone will be exactly at the temperature of 925 degrees Celsius. Why? Because you will see on the next slide. This is the temperature where we have the drop of the hardness, of the micro hardness, and also we have the drop of the grain size. And that's how we conclude that the temperature must be exactly 925 degrees Celsius. So we did all the necessity testings, like tensile testing, hardness measurement, measurement of impact toughness. And after all those testing, we went to the optical microscopy to see what will happen with creep in the region of the grain boundary and inside the grain. So, the optical microscopy, for example, this is the example of the coarse grain. As you can see, at the temperature over 1300 degrees, we have a pretty coarse grain, as you can see on the optical microscope. But our temperature is in the critical region where the grain is very fine, and here you can see that this structure at the same optical microscopy shows the very fine small grains, and also we can see the carbides here. But in order to see the placement, the exact placement of the carbides inside the grain, we had to put it, the specimen, to investigate it through the SEM, electron microscopy. Yes, and so here you can see the distribution in white color. You can see the distribution of carbides. So we can say that we have isolated islands of carbides here, like the kind of islands of carbides. But the last step in our investigation show us the solution of our problem. It was the TEM microscopy, the transmission electronic microscopy. As you know, the transmission electronic microscopy can show you really the scales of about some hundred of nanometers. It means 0.something micrometers. And thanks to this technology, we can see the exact grain boundaries, as I show you here, grain boundaries. And we can also see the structure of our material, which consists of lots. And here is, for example, one lot, and here is the lot boundary. Why this boundary is so important? Because if we have the carbides which precipitate on the love boundary, they will drop the strength of the steel. If we have the carbides here, if we have the carbides which are precipitated inside the love, it is not so dangerous for creep. What is dangerous is this. On the boundary of the love, and in these points here, when we have the meeting of three lots, this is something which is very dangerous in the terms of creep. Okay, here is a very nice slide when you can see the precipitating over the grain boundary. So this precipitating is a really big area. So let's see the conclusions. speak about intercritical heat effect zone in the steel named P91. This is the weakest microstructure with respect to trip resistance. So the performed analysis has shown that the smallest grains were formed at a temperature of 925 degrees Celsius. We can choose to make a post-weld heat treatment. This is post-weld heat treatment, or not to make. So we did both types of experiments. Without post-weld heat treatment here, we saw that without post-weld heat treatment, our steel is extremely prone to the brittle fracture. Why? Because if we do not perform the post-weld heat treatment, we will have a very high level of residual stresses. And residual stresses are extremely dangerous when you have the carbides which are precipitating in the grain boundaries. So they will fracture in the brittle manner. But that is why the post-weld heat treatment is necessary to be performed with every grade of steel P91, because those test results reveal the presence of precipitate at the grain boundaries, and these precipitates interfered with plastic deformation processes at the grain boundaries, and so they increase the trip resistance. In the case that we do not have post-weld heat treatment, no precipitation was found at the grain boundaries, but only at the lath boundaries, and so the resistance against plastic deformation at those grain boundaries was much lower, so the steel was prone to the brittle fracture. And to conclude our work, the post-weld heat treatment is absolutely necessary for the steel grade P91 if we want to make components for the elevated temperature application. This is it. Thank you very much for your kind attention. Because previously
but usually structures, doesn't matter.
I think you represented many information about the material, about the wind. Also, I think the temperature is the most important to know to create or to create the crack. What do you think about, for example, to change the thickness of pipeline and also the reduce or to reduce the part of welding, for example? I think there are also many types or many forms of welding. For example, sometimes for example, the surface. My question: what do you think to reduce the thickness of pipeline and to reduce also the part of welding?
Yes.
Thank you very much.
Calculate, when you calculate the strength of a component, then you are dealing in this conservative method. You are dealing only with loading, with stresses, and with the safety factor. But if you want to incorporate in your calculation the thickness of the material, so you have to do much more, for example, fracture mechanic calculations. In fracture mechanic calculations, if you involve, for example, C star and CT integral calculation, then you can try to decrease the wall thickness. The problem is with investors. If I come to an investor and I said him, no 45, you can be brave and try to do with only 30 millimeters, he will said, no, it's better for me. I'm safer if I put the thinner than a thicker pipe wall. So in the practice, this is not possible. But in the laboratory, we can do this. But if you go to the field, to the practice, you have to be careful, and you have much more problems with investors.
It will be political problems. Let's say
Or political problems,
Okay.
yes.
Thank you very much.
Thank you once
We
again.
have to
Thank
stop.
you. Okay.
Professor Bosic from University of Croatia, and he talks about fracture mapping and analysis of plates with motifs and the relational testing. Please.
Thank you. Thank you, Mr. Chairman. Good afternoon, ladies and gentlemen. Assalamu alaikum. It's my pleasure to be here. And it's my second time to be here in Algeria, and last time it was in Oran when I presented about fatigue of Stephen panels. So now it's natural follow up to speak about fracture of plates and Stephen panels. Before I start, I wish to thank you to the organizer, particularly to Professor Valeriani, who invited me here for kind hospitality, and I really feel here like at home. So thank you for your hospitality. It's always nice to mention our students who helped us with presentations and simulations. So for this work, these two young men helped me a lot. So after a brief introduction and some basic background, I will speak about experimental and numerical simulation results. So at first I will mention material and tensile and fracture properties of this aluminum alloy, which was considered. Then we present some experimental fracture analysis results, and then finite element simulation results and fracture analysis, and we'll compare simulations with experimental results. Basically, I will speak about fracture of plates and Stephen panels exposed to lateral pressure. And we will see in some examples to which kind of structures are these specimens related. So, in total life of a structure, we, as you know, distinguish crack initiation period, then crack growth period, and final failure. Today I will speak about this last stage here, and for this stage, a possible fracture mechanics parameters which can be used are critical sensitivity factor, or J integral, or CTO, or D, and some others, of course. This is how Shearer specified total fatigue life of a component and structure. Where do we find plates and Stephen panels? A typical example is aircraft fuselage, fuselage of an aircraft structure, and here we will see well-known example of Aloha point 737, which happened in 88. The problem here was so-called multi-site damage, which occurred at several adjacent holes, rivet holes, and then cracks after they were initiated, they grow, and then they cracks collide. And to crack collisions, large-scale damage appears. So this is described in the book by Chichiva, and a similar problem was observed later in ship structures. So if you look at this anchor, which is shown here, you see this white line. So I ask people, what is it? They say it's salt or it's dirt or whatever. Actually, this is where a very large crack occurred. So, similar in aircraft structures, cracks occur at stress concentration sites where you have geometrical discontinuities. So, this is a typical example. What you see here is deck structure turned upside down. So, compared to this here, so you can see stiffness here, stiffened panels, and also bulkheads. So where we have connection of this structure locally, we have discontinuities and stress concentrations, and we have this at several locations. So cracks initiate, propagate, and collide, similar as we had in case of Aloha aircraft. And when cracks become very large, like here, then fracture can occur. Luckily, this ship was not lost, but some other ships were lost. So what we investigate is influence of multiple site damage on residual strength of such a structure. And since we have large plastic zones here, large plastic deformation, then we use a lot of plastic fracture mechanics parameters And this is what we obtained in the experiment. So this plate failed at the highest pressure, and this at lower pressure, this still at low, and this at the lowest pressure. So actually stiffness decreased stress concentration and caused pressure at fracture at lower pressures. And now we have shell elements in our model, and we later lost around 3D elements. So this is first specimen with one crack. We need to model only 1/4 of the specimen due to symmetry. Plate with 3 cracks. So actually we have 3 crack tips. There on the other side we have the rest. So this is stiffened panel with 1 crack and stiffened panel 3 cracks. And because of bending, we wanted to see better how behavior of the stress strains to the thickness. So we introduced this model as well. So again, we have 3D models. And after we performed analysis, we compared measured strains with simulated strains. That's between 2 stiffness or between 2 cracks. For specimen with 1 crack. And this is at the top of the stiffener. So we put at the top of the stiffener of a side stiffener. So we can say that we got reasonable agreement of strains simulated measure, which is important for us. And the next step is to estimate critical pressures for specimens, pressure specimens based on fracture toughness properties obtained for central inertial plate. So it was, we remember it was like 360. So then we increased pressure and calculate K crack tips for all specimens, and we obtain these curves here. So then we say that this pressure, when we reach this critical value, that's fracture pressure. And then we compare this to experiments. So for shell experiments, this is what was obtained in the experiment. And for this is what was mentioned for shell. What was simulated by using shell elements. Will be a lower here, a bit higher. So anyway, a reasonable agreement is obtained by using shell elements. That's what based on JC, and that's based on CQB. Similar results are obtained again for shell elements. And it seems that 3D analysis will give a better result. We are conservative in all cases here. That's based on J integral, and that's based on CTOD values. And just to show you stress distribution for shell elements and 3D models. So it's pretty similar stress distribution, and that's for stiffened panel specimens. And then I will come to conclusions. Basically what we did, we showed that this shell element analysis, shell element, the 3D elements give similar results. That's very good because it's much easier to model structure with shell elements. And so it's a good information for us. And it was observed that a good agreement was achieved compared to experimental results. So such a straightforward procedure can be, we think, implemented to a real thin well structure for fracture analysis. And I have just one more slide here, since I guess I have like 2 or 3 minutes more. Or yeah, it's an event which will be next year in Dubrovnik in August. Yeah, this month. So I was around here. So many colleagues came in May to Dubrovnik for it 16. So we have good cooperation, I think, and not only Nigerian people, but all people from North Africa. So you are kindly invited to the next event, which will be actually 4 days in summer school, and International Conference on Structural Integrity and Durability. Thank you very much.
Thank you very much for this interesting and nice talk. And question more open on the issue.
Your work, because you talk about many things about materials, but my questions, you used ANSYS, but my opinion, I think that the abacus is more interesting than the ANSYS. That's one. Second part, I think you used normally a mesh and the surface but I think sometimes we must use a special mesh around the car, a ravine, in order to get a good result or a real result. Thank you very much.
Thank you very much. I explained sensitivity analysis which we carried before we started with the application of our model to this particular example. And also, when we analyzed fatigue, then we used linear elastic fraction mechanics, and this was elastic plastic fraction mechanics. So we learned a lot through linear elastic fraction mechanics modeling, and also there are some recommendations from software which meshes should be used, and we always compare this with analytical results for certain geometry which are well known before we apply this to our specimen. So in this case, we were really cautious about this. And when we speak about elastic plastic fraction mechanics here, there is also another work when we, for this fracture specimen, we compared analytical solutions with numerical. So analytical solution provides limited results because it cannot take into account this nonlinear behavior when we have low drop. So it helped us to calibrate our models, and we use later this model. So more or less we trust our models when we speak about J and C CTO which we calculated. I agree with you, it's absolutely important to calibrate system before we apply it to specimens.
Last question, please.